Good morning, all of you. Welcome to Sri Jayendra Rank Zone. In the previous class, we have done about important models of pH. In this class, we are going to do much about ionic equilibrium and some more problems regarding pH values. So, we'll continue with a new topic in this lecture. Please listen carefully, all of you. So, this is lecture number 4 in ionic equilibrium. Let us start now. pH of weak acid solution. Next topic is what? pH of how to calculate pH of weak acid, that is monopotic acid solution. So pH of weak monopotic acid solution, that is called pH of weak acid. Weak acid does not dissociate at 100%. Therefore, we have to calculate the percentage, that is Ks dissolution, using dissociation constant of the acid. So we have to calculate the percentage using Ka value. And for this, we have to use Ostwald's dilution law as we have derived earlier. So let us take one weak acid, that is Ha. Initial concentration is C, and initial concentration of H plus and OH minus. This should be H plus and A minus. It's not OH minus. It should be H plus and A minus. So please change it off. It should be H plus and A minus. And here also I'll change it A minus. So Ha gives us H plus and A minus. And at equilibrium, what happens? This becomes C into 1 minus alpha, C alpha, and C alpha. So then Ka is equal to C alpha square by 1 minus alpha. Ka is equal to C alpha square by 1 minus alpha. In this way, we will calculate dissociation constant of weak acid. Continuation. If alpha is less than 1, 1 minus alpha is equal to 1. So Ka is equal to C alpha square. So alpha is equal to root of Ka by C. And by this you can say concentration of H plus. This formula is most important. This already have given in the last previous class. Concentration of H plus is equal to C alpha. So since alpha is equal to root of Ka by C, by squaring we get concentration of H plus. How to calculate concentration of H plus? Root of K into C straight away. So pH is equal to 1 by 2 pKa minus log C. So pH is equal to 1 by 2 pKa minus log C. Even you can use this formula also to straight away calculate pH value. So pH is equal to 1 by 2 pKa minus log C, because 1 by 2 why you got, because this is square root and K is nothing but pKa minus log C, so that we can get pH, because H plus is equal to root of K into C. So pKa minus log C, because into is there, so minus log C. So on increasing dilution, C decreases, the concentration decreases, and degree of dissociation increases, and H plus concentration decreases, pH value increases. All these 4 points are very, very important. Please note down. Again, I repeat, on increasing dilution. So if you dilute the given solution by adding water, then automatically the concentration decreases. This is called, C is called what? Concentration. Concentration decreases, degree of ionization increases, or degree of dissociation increases, that is alpha increases, and H plus concentration decreases, and pH value increases. This is very, very important. Please note down. So to straight away, when they have given Ka and log C, when they are given Ka and C, straight away how to find pH? By using the formula pH is equal to 1 by 2 pKa minus log C. This formula is very, very important. Please note down. And these 4 points also important. What is this first point? On increasing dilution, the concentration of the solution decreases, the degree of dissociation increases, that is alpha increases, H plus ion concentration decreases, and finally pH value increases. So this is the relation between C, alpha, H plus, and pH for dilution. So on increasing dilution, this is very, very important formula. Please note it down. To find concentration of H plus ions, use the formula root of K into C. And to find pH, pH is equal to 1 by 2 pKa minus log C. pKa means how to find pKa? pKa is equal to negative logarithm of Ka. And log C is equal to, log C means log value only. So in this way you have to find. So this formula is most important. Please note it down. Next, Calculate pH of 10 to the power of minus 1 molarity is acetic acid. Take Ka is equal to in 10 to the power of minus 5. So they have given dissociation constant of acid, that is acetic acid, is given as 2 in 10 to the power of minus 5, and they are asking us to find pH value. So as I told you, pH is equal to 1 by 2 into pKa minus log C. What is pKa? Negative logarithm of 2 in 10 to the power of minus 5. So first we will find pKa is equal to minus log Ka, which is equal to minus 2 in 10 to the power of minus 5. This is can be calculated as minus 2 in 10 to the power of minus 5. So minus 2 into 10 to the power of minus log, 1 minute. Here it is not visible, so I'll write here minus log Ka. So it is equal to minus log of 2 into 10 to the power of minus 5, which is equal to 5 minus log 2. 5 minus log 2. That is 5 minus log 2 is equal to 5 minus 0.3010. 5 minus 0.3010, which is equal to 4.699. This is value of pKa. Now pH is equal to half into, so 4.699 minus log C. Log C is equal to log 10 to the power of minus 1 is equal to 1 log 10. So it is equal to 1. Is equal to how much? Equal to 1. So that is equal to 4.699 minus 1, that is 3.699. 1 by 2 into 3.699, which is equal to approximately 3.699 divided by 2. So it is equal to 2.85. Approximately it is equal to 2.85. 4.699 divided by 2 is equal to, so you'll get the answer in this way. So this formula is very important. Minus log C. Log C means minus log of 10 to the power of minus 1. Minus log 10 to the power of minus 1 is plus. So it is equal to plus. Wait. So it is 5.699 by 2. 5.699 by 2, it is equal to 2.85. 2.85 approximately, because it is minus log C becomes minus of log 10 to the power of minus 1. So it is equal to minus of minus 1, it is plus 1. So it is plus 1. 4.699 plus 1, it is 1 by 25.699, it is equal to 2.85. In this way, you have to calculate straight formula you can use. So answer is 2.85. 2.85. Very, very important. Please note down this formula. pH is equal to 1 by 2 pK minus log C if they are given K values. Easy to understand. Next question. So next concept. pH of a solution of a polyprotic weak acid. pH of a solution of a polyprotic weak acid. Diprotic acid is the one which is capable of giving 2 protons per molecule in water, just like H2SO4. H2SO4 is diprotic because it has the capacity to give 2 protons. For example, I'll write it here. H2SO4, if you take into consideration, or H2SO4 or H2A dissociates in water to form 2H plus. So it has capable of giving 2 protons per molecule in water. So let us take weak diprotic acid H2A in water whose concentration of C is molar, that is C. So in an aqueous solution, the following equilibrium existing: alpha 1 degree of ionization of H2A in the presence of HA minus, and alpha 2 degree of ionization of HA minus in the presence of H2A. So it forms 2 H plus ions. So Ka1 for first ionization constant of H2A, and Ka2 becomes second ionization constant of H2A. Since it is giving 2 H plus ions, so we can say Ka1 is the dissociation first ionization constant of H2A, and Ka2 is the second ionization constant of H2A. Continuation now. So H2A gives rise to HA minus plus H plus. This HA minus further changes to A minus to H plus. So it is giving first case C alpha 1, second case C alpha 1 plus C alpha 1 into alpha 2. So by substituting these values for diprotic acid, Ka1 and is less than Ka1 and alpha 2 would be smaller than alpha 1. So 1 minus alpha 2 is equal to 1. 1 plus alpha 2 is equal to 1. So on the whole, H plus concentration is equal to C alpha 1. H plus concentration is equal to how much? C alpha 1. So for di or polypoisic acid, H plus or pH can be calculated by using its formula. Very, very important. Use this formula for calculation of first equivalent constant alone. Take it as Ka1 is equal to C alpha square by 1 minus alpha. But in the numericals, we will substitute differently. That also I'll show you now. Next, factors affecting acidic strength. The extent of dissociation of an acid depends upon the strength and polarity of HA bond. In general, when the HA bond, that is hydrogen and another atom, bond in decrease, that is the energy required to break the bond decreases. HA becomes stronger acid. So it becomes more stronger acid. So weaker the bond energy, stronger is the acid. Also, when HA bond becomes more polar, that is the electronegativity difference between the atoms of hydrogen and A increases. There is marked change, there is marked charge separation. Cleavage of the bond becomes easier, thereby increasing the acidity. So by this, what you can understand, one point number one, the extent of dissociation of an acid depends upon the strength and polarity. So as the bond strength, simple words, I'll tell you in simple words, as the bond strength decreases, bond energy or bond strength decreases, acidity, acidic character increases, acidic character increases at the other words, it is strongly acidic. So please note down this, decreases and increases. Similarly, what is second one? As the polarity increases, polarity means the electronegativity difference between the two combining atoms increases, polarity increases, acidic character also increases. Acidic character increases. This is very simple. So instead of reading the whole part, you can use these two. As the polarity increases, acidic character increases because more easily it can separate in the water, because polar means it is more soluble in water. So as it is more soluble in water, definitely they'll yield ions easily. So which one form ions easily? That is strongly acidic character. So polarity increases, acidic character increases, bond strength increases, decreases, acidic character increases. So these are the factors affecting acidic strength. So the extent of dissociation of acid depends upon strength and polarity of the HA bond. So regarding strength, if you take bond strength, that is bond energy, as the bond energy decreases, acidic character, that is strongly acidic is the character. And as the polarity increases, the electronegativity difference between the atoms of H and A increases, due to which what happens? Easily they can cleavage, they can undergo cleavage, the bond becomes easier, thereby increasing the acidic character. So as the polarity increases, acidic character increases. As the bond strength decreases, acidic character increases. So please remember these two, very, very important. They can ask in the entrance examination. So that is factors affecting acidic strength. Factors affecting acidic strength. So instead of reading the entire matter, simply you can remember these two. That is bond strength decreases, acidic character increases. Polarity increases, acidic character increases. Polarity increases, acidic character increases. These are the things you have to remember. Very, very important. So please note down. Next continuation. As the size of A increases down the group between HA, like for example, if you take hydrogen fluoride, HCl, Br, and HA, as the size of A increases down the group, HA bond strength decreases and also the strength, acidic strength increases. So this is the acidic strength. So in between hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide is more acidic. Hydrogen iodide is more acidic because the A size is increasing, that is iodine size is bigger. Iodine is bigger in size. Iodine is bigger in size. So HI is more acidic since iodine is bigger. in size. So as the size of A, what is A here? A position means iodine. Increases down the group. You know, fluorine is greater less than size of the fluorine is less than chlorine, less than is far less than bromine. Bromine is far less than iodine. So iodine is more acidic in this group. Next is H hydrogen bromide. Next is hydrogen chloride. Next is HF. So HF is a weak acid when compared to hydrogen iodide because as the size of A increases down the group, the bond strength decreases. Easy to break the bond between hydrogen and iodine when compared to, very important point. Listen carefully. The energy required to break the bond between hydrogen and iodine is less when compared to the energy required to break the bond between hydrogen and fluorine. So automatically hydrogen iodide is becoming strongly acidic when compared to hydrogen fluoride because as the bond strength decreases, acidic strength increases. As the bond strength decreases, acidic strength increases. Next continuation. So these are the factors affecting acidic strength. Second one, as the electronegativity of A increases, the strength of acid also increases. So when compared to hydrogen, if the electronegative atom is more, so that is A value is electronegative value is A is high, automatically it it leads to the formation of it is more polar. As polarity increases, what happens? Acidic strength also increases. So it is internal factor again. As the electronegativity of A increases, polarity increases. Polarity increases. As the polarity increases, strength of acid increases. So, for example, methane is less acidic than ammonia, than water, than HF, because the fluorine is most electronegative atom. Next is oxygen. So, electronegativity is less for carbon when compared to nitrogen, oxygen, and fluorine. Here, what are the elements we have? Carbon, nitrogen, oxygen, fluorine. When carbon is combined with hydrogen, it forms CH4. When nitrogen is combined with hydrogen, it forms ammonia. When oxygen is combined with hydrogen, it forms water. And similarly, fluorine, it forms HF. So, in all these things, what happens? Fluorine is more electronegative. As the electronegative character increases in place of A, automatically the acidic strength increases because the polarity increases. So, the answer is for this, HF is strongly acidic than water. Water is strongly acidic than ammonia. Ammonia is strongly acidic than methane. So, in this way, these are the factors affecting acidic strength. Mainly, we have three factors that I'll write in the recap. So before going to this, mainly it affects strength of acidic character increases. First one, factors affecting strength of acid. First one, as we discussed, it is bond energy. Lesser the bond energy, stronger is the acidic strength. Second one, polarity, greater the value of polarity. And third one, size of anion. As the size of anion increases, acidic character increases. And fourth one, electronegativity. As the electronegativity of A increases, electronegativity of anion, the electronegativity of anion increases, also acidic strength increases. So these are the main four factors. These are the main four factors affecting the acidic strength. So I hope you understood. Next continuation. So please note down in your classbook bond energy, polarity, size of anion, electronegativity of anion. Size of anion and electronegativity of anion. Continuation now. What is common ion effect? The extent of ionization of a weak electrolyte is decreased by the addition of strong electrolyte. This already we discussed to a small extent. Now we'll discuss the complete topic of this. The extent of ionization of weak electrolyte is decreased by the addition of strong electrolyte which has an ion in common with the weak electrolyte. Example, addition of ammonium chloride to ammonium hydroxide. See here, ammonium chloride. If you add a little amount of ammonium chloride, ammonium hydroxide to ammonium chloride, so what happens? It suppresses the ammonium chloride. It suppresses the dissociation of ammonium hydroxide because the both in both the things, what is common? NH4 plus, NH4 plus. So addition of ammonium chloride to ammonium hydroxide solution decreases the dissociation of ammonium hydroxide because due to common ion effect, that is NH4 plus in both. Similarly, addition of sodium acetate to acetic acid will suppress the dissociation of acetic acid. This I have showed you yesterday only in the previous class. Addition of sodium acetate to acetic acid will suppress the dissociation of acetic acid, will suppress the dissociation of acetic acid. So these are the things. This is called common ion effect. So what is the formula of sodium acetate? CH3COONA. CH3COONA, and acetic acid is CH3COOH. So the common ion in these two is acetate ion, that is CH3CO minus. Is a common ion. And due to this formation of this common ion, it will suppress the dissociation of acetic acid. Suppress means it will not make happen the dissociation of acid in the same way like in the case of base. Decreases the dissociation of ammonium hydroxide. So this is called common ion effect. This is called common ion effect. So let us see common ion effect example now here. I'll show you. First, as I told you, ammonium chloride. First case we'll see now. First, we know ammonium hydroxide. When dissolved in water, it forms ammonium ion plus OH minus ion. And this, when you add a little bit of ammonium chloride for this, what happens? It dissociates to form NH4 plus and Cl minus. So this NH4 plus combines with NH4 OH minus, and again it forms NH4 OH. This NH4 plus combines with OH minus, and again it forms ammonium hydroxide, means suppressing the dissociation of ammonium hydroxide, suppressing the dissociation of ammonium hydroxide. So in this way, you can easily, this is called common ion effect. What is this called? Common ion effect. What is the common ion in these two? Ammonium plus ions. So this is very, very important concept. So please note it down. So by the addition of small amount of ammonium chloride to ammonium hydroxide, the dissociation of ammonium hydroxide can be decreased. Similarly, by the addition of sodium acetate to acetic acid, the dissociation of acetic acid can be suppressed. This also we have done in the previous lecture. So this is called common ion effect. This is called what? Common ion effect. Next, we have important concept, pH on dilution. pH on dilution, very, very important. Some concepts are missed in this, so that's why I'm writing here. So please note it down. So pH on dilution. So what happens to the pH of a substance on dilution? For example, let us see now. The pH of HCl is monobasic acid, so monobasic acid only is, let us say it is equal to 3. It is diluted to 100 times. Calculate the resultant pH. Calculate the calculate the resultant pH of the solution. pH of the solution. Why I'm writing this numerical so that you can understand what happens pH to pH on dilution. So the pH of HCl is 3. It is diluted to 100 times. Calculate the resultant pH of the solution. So for this, let us take, since pH is equal to, I will write the solution for this. Solution in blue color, if you write, it will be easy for you to understand. So now I will write the solution for this. Please listen carefully. Solution, this model is very, very important for all competitive exams. So since pH is equal to, pH of HCl is equal to 3, means then concentration of H plus concentration becomes 10 to the power of minus 3, since already we know. And it is diluted to 100 times. So new concentration, H plus new concentration is equal to, after dilution, 10 to the power of minus 3 by 100. So it becomes 10 to the power of minus 5. 10 to the power of minus 5 because it is diluted 100 times. So therefore, pH of the resultant solution is equal to minus log 10 to the power of minus 5 is equal to 5. So by this, what you can understand, the value of pH value increases upon dilution, and more important, H plus concentration H plus concentration H plus concentration decreases on dilution. So please note down these two concepts, very, very important. So in this way, we have to calculate when pH of a given solution is diluted. Similarly, we can say base also. For example, we'll see for base also. Let us see for base, what happens for base. Now this is in the case of acid. Now let us see for base. We'll see, let us see now for base. pH upon dilution for base. pH upon dilution for a base. Let us see now. So for this, let us take one consideration. The pH of ammonium hydroxide solution is ammonium hydroxide solution is 10. Just write it clearly. Is 10. It is diluted to 100 times, again same I'm giving. Calculate the resultant pH. Calculate the resultant pH. So since it is a base, first I'll do the solution now. So what is the question here? Again, I'm repeating. The pH of ammonium hydroxide solution is 10. It is diluted 200 times. Calculate the resultant pH. So after diluting ammonium hydroxide solution, what happens to the pH of ammonium hydroxide solution? So let us see. This is called pH upon dilution for base. Now let us see. Since pH of ammonia is equal to 10, implies POH is equal to 14 minus 10, because since it is a base, we have to consider POH only, equal to 4. Since POH is equal to 4, implies concentration of OH minus is equal to 10 to the power of minus 4. Concentration of OH minus is equal to 10 to the power of minus 4. Now for this it is diluted to 100 times. So concentration of OH minus, so OH minus on dilution. So concentration of OH minus on dilution. After dilution, you can just see it is equal to 10 to the power of minus 4 divided by 10 to the power divided by 100 is equal to 10 to the power of minus 6. So by this implies POH is equal to negative logarithm of 10 to the power of minus 6, which is equal to 6. Implies pH is equal to 14 minus 6. It is equal to 8. So by this what you can understand, initial pH is 10. Final pH becomes 8. By this pH on dilution for a base decreases. pH for a base on dilution decreases. pH on dilution for a base decreases. Very, very important. For acid, the pH value increases on dilution. But base, the pH value decreases on dilution. Whereas OH minus concentration increases. No, OH minus concentration also decreases. So OH minus concentration decreases as well as pH value decreases for a base on dilution. This is very, very important. So please note it down in your classwork. Next. So I hope you have noted it down. So what happens to the pH of for a base if it is diluted? The pH of a base decreases on dilution. The pH of acid increases on dilution. The concentration of H plus ions decreases on dilution. The concentration of OH minus ions decreases on dilution. So H plus ion concentration decreases, OH minus ion concentration decreases on dilution. But pH value for base it is decreasing, and for pH value for acid it is increasing. So these are things you have to remember. Please make a note in your classwork. Next, what happens? Very important model in this I'll show you. Based on dilution only. Based on dilution. I'll write one important question. This is very, very important, this model. The pH of a monobasic acid. The pH of monobasic acid is 5. If it is diluted to 100 times. If it is diluted to 1000 times, let us say 1000 times. Calculate the resultant pH. Calculate the resultant pH. So, this is very important condition. Please note it down. I'll give the solution for this now. As usual, we'll do since pH is equal to, since pH is of the monoacidic as monobasic acid is 5. So it implies H plus concentration is equal to 10 to the power of minus 5. So new H plus concentration nu is equal to 10 to the power of minus 5 divided by 10 to the power of 3, that is 1000, is equal to 10 to the power of minus 8. So implies therefore pH is equal to minus log 10 to the power of minus 8 is equal to, according to this, 8. But it is not correct. Why? The pH of an acid, is always less than 7. pH of an acid is always less than 7. Therefore, new pH is equal to, resultant pH is equal to pH resultant is equal to approximately it is equal to 6.98. It cannot maximum exceed 7 also, because an acid can never become base on dilution. Acid can never become a base on dilution, because if it is taken as 8, resultant if you take it as 8, it becomes base, which is not correct. So since 10 to power pH of minus log of 10 to power minus 8 is equal to 8, so pH of an acid can never be 8. So since pH of an acid is always less than 7, so pH resultant equals 6.98. Acid can never become a base on dilution. So this model is very, very important. Even though you got the answer 10 to the power minus 8 and 8 also, take it as 6.98 or less than 7. That's our maximum. It is very close. Greater than 5, less than 7. Greater than 5, less than 7. So similarly, you find the same case in base also. This is very, very important. Please note it down in your classwork. This model is very, very important. Next continuation. So I have given enough time for you to copy. So please copy it down. I will do continuation. Next, very, very important concept. Some concepts are missing for advanced level. So that's why I'm doing all the things clearly in the form of PPTs. Next concept. So all these concepts, please note down in your classwork. Next, pH upon mixing. Next, what is the model? pH upon mixing. How to find pH upon mixing? For example, 50 ml of, just note down a numerical. Based on numerical only, it will be easy for us to understand. I'll just clear it now. Is also very, very important. I'll just give by problems. The pH of a solution, the pH of a solution obtained upon mixing 50 ml of 0.5 normality solution, 50 ml of 0.4 normality HCl, and 50 ml of 0.2 normality, 50 ml of 0.2 normality NaOH solution is. NaOH solution is. This is the question. So what happens when an acid is combined with a base? So for these things, we have to consider first milli equivalent of acid. Milli equivalent of acid is equal to 50 ml into 0.4 normality of HCl is equal to 50 into 0.4. It is equal to, just multiply it. So 54 is 200. So 50 into 0.4, it should be equal to 20. Similarly, milli equivalent of base, 50 into 0.2 is equal to 10. Since milli equivalent of acid is greater than milli equivalent of base, milliequivalent of acid is greater than milliequivalent of base, milliequivalent of base. So to find resultant concentration, resultant concentration is H plus acidic solution. Yes, I'll write here again. Resultant solution is acidic. So resultant concentration you can find out. Resultant concentration by adding these two. Resultant concentration is equal to M1 V1 minus M2 V2 by V1 plus V2. Or even N1 V1 also. Here in the case of normality they are given, so you can write N1 V1. N1 V1 minus N2 V2, because normality and molarity is same for monoacidic bases and monobasic acids. So we have to use this formula. So for example now, and here what is the value of N1 should take, which is highest. So acid is highest, so N1 should be taken for acid, N2 should be taken for base. So 20, that is 15 to 0.4 minus 20 into, 15 to 0.2 by 50 plus 50. So it is equal to 20 minus 10 by 100. That is 20 minus 10 by 100, which is equal to 10 by 100, which is equal to 0. So 10 by 100 is 0 0.1. 0.1, that is equal to 10 to the power of minus 1. So 0.1. Therefore, pH is equal to negative logarithm of 10 to the power of minus 1, which is equal to 1. Which is equal to what? 1. In this way, you have to find out. So this is called pH of solution obtained. So whenever an acid is combined with a base, you have to take minus. For resultant concentration, you have to take minus. And to decide which is N1 and which is N2, we have to consider milliequivalent of acid and milliequivalent of base. Suppose if milliequivalent of base is greater than milliequivalent of acid, then N1 should be taken as base and N2 should be taken as acid. Very, very important that. Otherwise, you'll get the values in negative. So 10 by 100 is equal to 0.1. So pH is equal to minus log 10 to the power of minus 1, which is equal to 1. So in this way, you have to calculate pH values upon mixing. So pH upon dilution, we know how to find, and pH upon mixing also we know how to find. So this is called pH upon mixing. Let us consider one more question based on this. So the pH of a solution obtained upon mixing 50 ml of 0.4 normality and 50 ml of 0.2 normality in our solution. Since they have given normality, normality and molarity is same for monobasic acid and monoacidic base. For dibasic, it is different. So pH of a solution obtained upon mixing 50 ml of 0.4 normal to HCl and 50 ml of 0.2 normal to NaOH solution is, so milliequivalent of acid first you have to find, it is 20, and milliequivalent of base is also equal to 15 to 0.2, it is 10. And in between acid and base, which is greater here? Acid. So resultant solution definitely becomes acidic. So as the resultant concentration is acidic, so we have to take N1 value, N1 V1 as acid and N2 V2 as base. Suppose if base concentration is more, N1 V1 as base and N2 V2 as acid by V1 plus V2. This is the formula for finding resultant concentration. So resultant concentration, if you get, that is equal to 0.1. So pH is equal to minus log of 10 to the power of minus 1, because 0.1 can be taken as 10 to the power of minus 1. So it is equal to 1. So in this way, you have to calculate the answer. It's very, very important. Please note it down. Now, so this is about pH problems. Next concept we'll discuss about buffer solutions, but remaining. So now in this class only we'll continue some more problems with pH values. Then we'll end up this session. So please listen carefully. Let us start now. Now questions based on today's concept. That is this lecture concept. Just note it down. The dissociation constants. The dissociation constants of two acids HA1 and HA2 are 4.5 into 10 to the power of minus 4, 4.5 into 10 to the power of minus 4, and 1.8 into 10 to the power of minus 6, minus 5 respectively, minus 5 respectively. If both are having equal concentrations, if both are having equal concentrations, in their solutions, the relative strengths of acids are the relative strengths of acids is option A, it is 5:2. Option B, it is 2:5. Option C, it is 5:1. And option D, it is 1:5. So just think about this question. Easily you can understand. Question number 1 for today's session. So they're asking us to find if both are having equal concentrations in their solutions, the relative strength of acid is given by. So to find relative strengths of acid, we need to find degree of dissociation. So alpha 1 by alpha 2 is equal to root of Ka1 by Ka2. That is root of K1 by K2. Root of K1 by K2. So what is Ka1? 4.5 into 10 to the power of minus 4 divided by 1.8 into 10 to the power of minus 5 under root. So this on calculation you will get is equal to, so 10 to the power of minus 5 goes to numerator, 10 to the power of minus 9. 4.5 10 to the power of minus 9 can be taken as 45 10 to the power of. So you can take 18 into 10 to the power of minus 6 and 45 into 10 to the power of minus 5. So minus 6 and minus 5. So after calculation you'll get it is equal to 5 by 1. Equal to what? 5 by 1. So answer it could be 5:1. So to calculate relative strength of the acids, we have to use the formula alpha 1 by alpha 2 is equal to K1 by K2. Please note down this formula, very, very important. Next question. So next question write down. So I hope you have copied this question and answer as well as. So please note down this calculation part. Do not have space. That's why I'm not doing. I think you can do it easily. If you don't understand also, you can raise your doubt in the doubt session and you can finish it off. Next. Question number 2. So what is the question number 2? This is very, very typical question. This has come for Neet as well as JEE Mains for 2 times. The pH of a 1 liter solution, 1 liter solution is 2. It is diluted with water. It is diluted with water till the pH becomes, till it becomes 4. Till it becomes 4. How many liters of water is added? How many liters of water is added? Option A, it is 99 liters. Option B, it is 100 liters. Option C, it is 999 liters. And option D, it is 1000 liters. So, you know pH upon dilution. So, we have to apply the same for dilution. So, now we'll see, let us see the solution now. Please listen carefully. Once again, I repeat the question. The pH of a 1 liter solution is 2. It is diluted with water till it becomes 4. How many liters of water should be added? So, first we'll say pH is equal to 2. Since pH is equal to 2, implies H plus concentration is equal to H plus concentration is equal to 10 to the power of minus 2. Similarly, second, pH new after dilution is equal to 4, implies H plus concentration is equal to 10 to the power of minus 4. 10 to the power of minus 4. So from 10 to the power of minus 2 to 10 to the power of minus 4 means it should dilute 100 liters. But already 1 liter is there. Already 1 liter is there. So to become from 10 to the power of minus 2 to 10 to the power of minus 4, we should add 99 liters of water only. Very, very typical question. 99 liters of water, because it's 1 liter, no one will see in the question. But here 1 liter is already there. So 99 liters of water should be added. We should add 19 liters of water. So the answer is first option. Very, very important question. Please note it down. So to make pH from 10 to the power of minus H plus concentration from 10 to the power of minus 2 to 10 to the power of minus 4, we have to dilute it by 100 times. And 100 times means 100 liters of water should be added. But already 1 liter is present here. So simply 99 liters of water is enough. So this is the answer. Very, very typical question and very, very important question. So please note it down. Next question. Question is based on today's concept. Very, very important question. Please note it down. Next question number 3. So I hope you have written. Next question number 3. Note it down. Equal volumes of two solutions. Equal volumes of two solutions with pH is equal to 3, pH is equal to 3, and pH is equal to 11 are mixed. The pH of the resulting solution is the pH of resulting solution is, this model is also important, the pH of resulting solution is, we need to find what is the pH of resultant solution. Option A is equal to 8. Option B, it is equal to 7. Option C, it is equal to 6. Option D, it is equal to 0. So we need to calculate resultant pH of the solution. So for this question, we have to use pH upon mixing. What do we have to use? pH upon mixing. Very, very important. So pH upon mixing. So for this, I'll give you an important note. So please note it down. An acid and base, an acid and base having equal volumes. Very, very important point. Please note it down whenever they are given like this. An acid and a base having equal volumes and equal strength and equal strength. Yeah, equal strength is also important. Only volumes it will not work out. When mixed together to give neutral solution. When mixed to when mixed, they'll give neutral solution. Neutral solution. Neutral solution. So for this, the answer could be second option, to give neutral solution. Neutral solution. So pH of neutral solution is equal to how much? It is equal to 7. Therefore, pH is equal to 7. So answer is second option. Here, an acid and a base having equal volumes and equal strength. How can we say about strength? Because the pH of acid is 3, pH of base is 11. Just they are exactly equal strength. That is in case of acid and base. So solution minus 1 by pH is equal to 3. Solution minus 2 by pH is equal to 11. So because how can we say strength? Since pH is equal to 11 for second solution implies POH is equal to 14 minus 11, that is equal to 3. So the basic strength is same and acidic strength is same, that is pH is equal to 3 and POH is equal to 3. So in this case, when they mix it together, an acid and base having equal volumes and equal strength. How can we say equal strength? Because POH value is equal to 3 and pH value is equal to 3. So when they mix it together, they give neutral solution. When mixed to give, they give, see here I write, they give neutral solution. So neutral solution, what is the value of pH of a neutral solution? It is equal to 7. Like these questions are very, very important. So please note it down. This statement is very important. Again, I'll repeat the statement. An acid and base having equal volumes and equal strength. Only equal volumes will not sufficient, is not sufficient. Equal strength also should be sufficient. An acid and base having equal volumes and equal strength. When mixed, they give neutral solution. So how can we say pH is equal to 11 for the second solution, that is base? So for base, we have to consider OH. So POH is equal to 14 minus 11, it is equal to 3. So 14 minus 11 is equal to 3 and pH is also equal to 3. So the concentration of H plus is 10 to the power of minus 3 and concentration of OH minus is also equal to 10 to the power of minus 3. So by this you can say, so here I'll write again, since concentration of H plus in case of acid is equal to 10 to the power of minus 3, also concentration of OH minus also equal to 10 to the power of minus 3. So these three concentrations as well as volumes are equal. When concentrations and volumes are equal for acid and base, the resultant pH becomes neutral solution. The resultant pH becomes neutral solution. So the answer is 7 because the pH of neutral solution value is equal to 7. So second option. I hope it is clear. Very, very important. This model, this statement is important. That's why I have discussed. Next question. Let us see now next question. Question number 4. If the Ionic product of water, Kw, is 1.96 in 10 to the power of minus 14 at 35 degrees C. Conceptual based questions, these are all. What is the value of, what is its value 10 to 10 degrees C? What is its value? What is its value at 10 degrees C? Option A, 2.95 10 to the power of minus 14. I'll make it clear. 2.95 10 to the power of minus 14. Option B, 1.96 in 10 to the power of minus 7. Option C, 2.95 10 to the power of minus 15. It's just concept-based question. You have to use concept properly. And option D, 3.9 10 to the power of minus 12. Now, so what is the expected answer? It could be, listen carefully now. Solution. Since already we know, as the temperature decreases, ionic product of water also decreases. Ionic product of water decreases. So at 10 degrees C, Kw value also decreases. Kw value decreases, not also, Kw value decreases. So in the options, which is the decreasing value, which is the least value, we have option, first option 2.95 10 to the power of minus 14, second option 1.96 10 to the power of minus 7, third option 2.95 10 to the power of minus 15, and fourth option it is 3.9 10 to the power of minus 12. So 10 to the power of minus 14 greater, lesser power is 10 to the power of minus 15. So answer is C. Directly we can say it is C. As the temperature decreases, ionic product of water also decreases. So at 10 degrees C, K value decreases, Kw value decreases. So if it is more than 35 degrees C, automatically it could be anything. So remaining all options are greater than this given value. So from the given value, it is 1.96 10 to the power of minus 14 at 35 degrees C. So at 10 degrees C, this should be lesser than this value. So lesser than this value is only one option, that is C. So these are all questions based on concept based questions. Very, very important. Very, very important. So please note it down. And next session we'll do buffer solutions. And so with this, I'm stopping this class. The next session, we are going to discuss buffer solutions, which is very, very important. So please do what we have discussed clearly, all the important points, because these points are enough for all competitive exams. So please follow. Thank you all.